Given an array of integers nums and an integer target, return the indices of the two numbers such that they add up to target. Each input has exactly one solution, and you can't reuse the same element.
Quick check on input and output. The input is the array and the integer target, and I should return a length 2 array of indices in any order, right?
Right.
And on constraints, the array is up to 10,000 elements, values can be negative, and duplicates in the input are allowed. I'll resolve duplicates by their indices, walking the examples to confirm. 2, 7, 11, 15 with target 9, answer 0 and 1. 3, 2, 4 with target 6, answer 1 and 2. 3, 3 with target 6, answer 0 and 1. Got it. Let me start with the obvious approach. Walk every pair I and j strictly greater than I, and return the pair whose sum equals the target. 5 lines of pseudocode. Outer loop on I, inner loop on j starting at I plus 1, early return on a hit, otherwise none. It's correct. Let me trace it on the example to confirm. Using nums 3 to 4 with target 6. Track I, j sum, and whether we have a match. OK, I is 0, j is 1. Nums I is 3, nums j is 2, sum is 5. Not 6, so I bump j. I still 0, j is 2 now. 3 plus 4, 7. Still off, j is at the end. Bump I. I is 1, j is 2. 2 plus 4, 6. That's the match. Return 1 and 2. So 3 pair checks for length 3. Worst case is n choose 2 quadratic. Fine for tiny inputs, but I should be able to do better. Honestly, I'd rather not write the brute force out. It's just 2 nested loops in Java, nothing tricky. The interesting question is whether the n squared can come down. Let me think about what's redundant in those nested loops.
Before you optimize, what question do I keep asking myself? Every iteration.
Yeah. What question do I keep asking myself? It's the same one each time. Have I seen target minus this value? If I record everything I've already seen, that question is just a lookup. Right, so a hash map from value to index. Walk the array once. On each element, check the complement first, then record yourself before moving on. Here's the algorithm in pseudocode. Map from value to index, single loop, complement is target minus current. Lookup first, write second. If the complement is in the map, return its stored index together with I. Otherwise, record the current value with its index. Lookup before write is the subtle bit. Otherwise, a value like 3 plus 3 with target 6 would match itself. Tracing on the same example, 3, 2, 4, target 6. Track current, complement, whether the complement is seen, and the map. I is 0, current 3, complement 3. Map empty, store 3 pointing to 0. I is 1, current 2, complement 4. Map has 3 but not 4, so store 2 pointing to 1. I is 2, current 4, complement 2. 2 is in the map at index 1, return 1 and 2. 3 iterations, 3 lookups done.
Looks right. Go ahead and code it up in Java.
Sure, so map of integer to integer for scene. Standard for loop over I. Inside the loop. Complement equals target minus nums of I, then contains key. If yes, return new int array with scene. Get of complement and I. Otherwise, wait, let me make sure I have the order right. Lookup before put, yeah, otherwise 336 matches itself. So the put comes after the if.
Good catch. What if the array contains duplicates, 3 and 3 with target 6?
Then the first 3 goes in at index 0. On the second 3, complement is 3, map has 3 at 0, we return 0 and 1. Distinct indices correct.
Walk me through the complexity.
Time is linear, 1 pass over n. Space is linear, at most n entries in the map. We've traded constant space for linear time lookups.
Quick follow-up. Suppose the input is sorted. Can you do better on space?
If it's sorted, yeah, the map isn't necessary. I drop it and use 2 pointers, one at the start, one at the end. If the sum is too small, advance left, too big, retreat right. Linear time, constant space.
Trace it on a small sorted example, so I see the pointer moves.
Sure, take nums 2, 7, 11, 15, target 18. Left at 0, right at 3. Sum is 2 plus 15, 17. Too small, so left moves to 1. Now 7 plus 15, 22. Too big, right pulls back to 2. 7 plus 11, 18. Done. Return 1 and 2. 3 iterations, no allocations.
Code it up.
2 ints left and right. While left less than right, compute the sum, branch on equality and ordering. Match returns immediately. Sum less than target, left plus plus. Greater, right minus minus. Each pointer moves at most n times in total, so the whole thing is linear, and we never allocate beyond the 2 ints.
Different requirement. Return every unique pair, not just one.
Okay, so the shape changes. The function returns a list now. I'd sort first if it isn't already, then on each pointer move skip equal neighbors to dedup. Sort dominates at n log n.
Sketch it.
Same 2-pointer skeleton, but instead of returning early, I append the pair to a list, advance both pointers, and skip duplicates with 2 inner whiles. Lines 12 and 13 are the dedup. If nums of left equals nums of left minus 1, the next pair would be a duplicate, so we skip ahead.
On embedded hardware, no hash map allocations allowed. What now?
Right, so I can't lean on a hash map. I'd sort and run the 2-pointer scan, but the catch is I have to preserve original indices. I'd pair value with index first, sort by value, then scan. Constant extra space if I'm careful, n log n total.
Walk me through the implementation.
Allocate an n by 2 int matrix on line 4. Column 0 is value, column 1 is index. Fill it in a single pass. Line 8 is arrays. Sort with a comparator on the value column. After that, the value column is sorted. Indices come along for the ride. Then the same 2-pointer scan over the pairs. On a match, line 12, return the original indices, not the sorted positions. If we wanted true 0 allocation, we'd switch to an in-place sort on the array itself and pre-record indices in a parallel buffer the caller owns.
Good. Pattern stays the same. Pair plus arithmetic relation reaches for hash map complement.